All right, what we're looking at here are the key aspects of magnetism and how charges relate to this concept of magnetism. So, the first thing that we're going to talk about is right here in the middle, what we call hand rule number one. Now, the idea here is that we discovered that moving charges produce a magnetic field, and this hand rule number one is essentially just a kind of clever way in our brains to remember what that looks like. So my awesomely drawn hand here, that is supposed to copy, you can tell it's exactly the same like that, right? So your left hand is used when we're talking about negative charges, which I'm going to use pretty much all the time because it's electrons that are typically moving. So the idea here is that your thumb points in the direction that the charges are moving. So electrons moving in the direction of the thumb. Your fingers in this scenario show what the magnetic field looks like due to that moving charge. So we're going to draw, essentially, it's a loop like so. So the idea is that when electrons move, that produces a magnetic field. That's the key important connection here, is that moving charges will produce magnetic fields. So if you had a wire, all right, so let's imagine a wire here, and that wire is carrying electrons this direction from the bottom towards the top of the screen. What does the magnetic field look like due to those moving charges? We'd use hand rule number one, put our thumb in the direction of the moving charges. Our fingers that wrap around it show that there would be a magnetic field surrounding that wire. So if we draw that, let me scooch this over, and we say, okay, here's my wire, and I have electrons moving in this direction. That means, again, hand rule number one, that magnetic field is encircling this wire, right? It's coming from behind the wire, around the front, and back around like so. What happens if the electrons stop moving? No more magnetic field, right? So again, moving charges produce magnetic fields. Where that becomes a little more interesting is when you have loops of wire. So bringing back the real piece of wire here, I'm going to draw what's supposed to represent a loop of wire coming towards us like that. So we're doing a little 3D drawing here. Okay, so this back part is like flat against the page, and this part of the loop is towards us. Okay, now what we kind of discovered here is that when you have loops of wire, that brings a uniform nature to the magnetic field that's produced here. Okay, so let's say again that electrons are moving upward in this wire. So they come up this wire, they come around, move towards us, go around this way, and then continue on like so. So the magnetic field, using our same hand rule, thumb pointing upward, magnetic field encircles the wire here, kind of the same thing we saw, nothing really exciting. Then as we go up the wire here, now this part is coming towards us, right? So there's magnetic field going around through the loop, around the other side. Okay, this front, now the electrons are going down, same thing, we have magnetic field going through the loop, and so on. Now what you'll see here is that magnetic field then is always going through the loop and out of the loop in this direction, right? There's a uniform setup to the way that the magnetic field is working. What's super cool is that we see the same sort of behavior in permanent bar magnets. So that idea of a magnet having a north and a south end are conventions that were kind of set up before we knew some of this stuff, is that magnetic field comes out of the north end of a magnet and goes into the south, right? Now, if you're wondering, like, why, what is that stuff? If you've ever seen pictures before of like iron filings sitting on a piece of paper near a magnet, the filings line up with these magnetic field lines. Or like if you put a compass in place here, the compass needle would line up with these magnetic field lines. Okay, so the big leap that we're making here, we're realizing here, is that a loop of wire will produce a magnetic field that looks exactly the same as a permanent bar magnet. So what in the world? What's going on here? Jump over to this electron orbits topic. If we imagine in the simplest sense just some electrons orbiting the nucleus in an atom, as electrons orbit around the nucleus, hopefully you can see that it's essentially a loop of wire. So as these electrons loop around, you could use your hand rule. In this drawing, the electron on the front side is going this way and then that way on the back side. So we'd have magnetic field encircling the orbit. And essentially, this single orbiting electron would make a magnetic field that would be like a loop of wire, that would be like a bar magnet. Oh wait, what's a permanent magnet? A permanent magnet made up of a bunch of atoms that apparently have their orbits well enough aligned to make the overall substance magnetic. Now that's kind of weird to say because every substance is made out of atoms. So does that mean that everything is magnetic? Well, yes and no. It means every bit of matter would have some sort of magnetic properties. But think about the trillions and zillions of atoms that make up, even the smallest things. So in this bar magnet, imagine that there's little zones, and within each little zone, you have the orbits mostly aligned so that overall there's a uniformity to the magnetic field to make the overall thing magnetic. For some reason, there are only a few elements on the periodic table that are really good at having matched orbits like this on the macro scale, on the large scale. So iron, neodymium, there's a few things that are good at having aligned orbits. So to just pause and summarize here, moving charges produce magnetic field. We see that whether it's a single charge or a flow of electrons in a wire. Wow, that's cool. If you make a loop, it makes the magnetic field uniform like we see in a bar magnet. Oh wait, what's a bar magnet? It's the same idea. It's due to electron orbits being aligned and making the overall magnetic nature this big magnet. We can get the same thing with loops of wire stacked up on top of each other. So in here we drew one loop. Well, if we had loop, 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 and out, then that would make an even stronger overall field that would be going into one end and out the other end. All right, so you can start to see the basis of what an electromagnet is. Okay, so we're going to make another jump. How do magnetic fields interact with other charges? So I've got some other stuff for us to take a look at here. The first thing that we're going to look at is what I call hand rule number 2. Okay, and like we talked about up there, it was the discovery of how things are working. So what we discovered here, what we're going to represent with hand rule number 2, is that moving charges will interact with pre-existing magnetic fields. Now, that should make kind of good sense because we see here that a moving charge creates a magnetic field. So that means if you send a moving charge through a magnetic field, those fields will interact and you'll have some sort of force. So this drawing is to help keep track of how that works. So the thumb, just like before, points in the direction of the moving charge. Again, you use your left hand if it's negative charges. It would be right hand for positive, but we don't see that happening as often. The finger, your index finger, because again, this is like this, my 3D, these 3 fingers are pointing towards you. The index finger is the direction of the external magnetic field. Why magnetic fields are B, who knows? It's one of those physics things that just drives us crazy. The three fingers are the key here. The three fingers point in the direction of the force on the moving charge. Finish writing that. Okay, so trying to put all that together. If you have an electron moving through an external magnetic field, there will be a force on that moving electron due to this field. Okay, now that probably seems really like abstract, hard to imagine. So let's look at a couple of scenarios. The first one is just a single charge moving through a magnetic field. Okay, keep it simple. So we're going to draw a magnet here. Okay, get my 3D skills on again. So we're imagining this is like a horseshoe magnet. Okay, so this is coming towards us, and then this part is behind. Okay, now let's say that this is the north pole of the magnet, and back here is the south pole of the magnet. Our conventions going way back up, back into here. This idea is that magnetic fields go from north to south. So just this magnet on its own, forget any other things, just this magnet on its own has magnetic field that would go from north to south. All right, so you'd have these field lines arching all over the place. Now, let's add the charge. Let's say that we shot a single electron with some kind of fancy electron gun so that it went right through that magnetic field. It goes right through the middle of this horseshoe magnet. What's going to happen? According to hand rule number 1, that moving charge has its own magnetic field. According to hand rule number 2, because of this charge's magnetic field interacting with this magnetic field, there will be a force on that moving charge. So now we just have to line up our hand rule. Thumb points in the direction of the moving charge. Finger points in the direction of the magnetic field. In my drawing, I'm saying north is front, south is back. So I have to orient my hand kind of like this. The three fingers, which if you look, I have like an X, Y, Z axis. The three fingers are pointing down. That means the force on the charge is down as it goes through here. This electron would get curved in that direction as it shot through the magnet. If you moved the magnet into different orientations, you could control the path of these electrons. Okay, now let's amp up our situation here. Let's say that now we have a wire which would have a current flowing through it, and we're going to have that in the presence of a magnetic field. So let's see, let's draw this one slightly different here. Let's say that we have the end of a magnet right here. Here's the north end of the magnet. Then above it, the rest of a magnet, right? Here's the south end. So this time we're drawing kind of up and down instead of the 3D here. So magnetic field going from north to south. Now let's say that there's a wire that passes right through the center of here, and that wire is carrying electrons moving in this direction. According to hand rule 1, those electrons would have a magnetic field surrounding it. According to hand rule 2, that would cause a force on those moving charges, even though they're in the wire. Hand rule 2, thumb goes in the direction of the electrons. Finger points in the direction of this external field, these lines I drew. So now my three fingers, I have to rotate for you to see, three fingers are pointed downward, right? So if we turned this on and had this current flow through this wire, that wire would get pushed in that direction into the page or into the screen from this drawing perspective. Okay. All right, last scenario. I've got to scooch this up so you can see it. What if we move a wire through a magnetic field? So in this case, we forced a current. This last scenario is no external voltage. We just have a wire and we're going to move it through a magnetic field. Okay. So I'm going to use this same drawing again. I'm just going to erase this part of it. Okay. So we've got a wire. Now, it looks like it ends here and here, but pretend like it just keeps going on whatever in these two directions. We've got this wire and we're going to move it. Okay, we're going to move it manually. Imagine that we grabbed the wire and we pulled it like this direction. We pulled it out of the screen. Okay, we're pulling it this way. How do we connect that to the hand rule? Well, essentially, if we grab the wire and we pull it this way, we're moving all of those charges in this direction. So using my left hand again, because we're talking about the electrons that can move, we're going to put our thumb pointing this way, because that's the direction we're putting all the charges. We're making a move that way. The external field that they're in is pointed this way. It's the purple lines. A force would act on those charges in the direction of these three fingers. There would be a force acting that way. A force acting that way on all the electrons. So what are the electrons going to do? They're going to move that way. So if we grab the wire and pull it up, we've actually produced a current in the wire by moving the wire through this field. This isn't due to some battery on the outside. It's a voltage caused by these interacting magnetic fields. Okay? So, lots of stuff here. Hopefully that clarifies lots of little tidbits and helps pull it all together. At the top, we talk about the origin of magnetic fields and the idea of electromagnets and permanent magnets and how that's connected to moving charges. Down here, we have the foundation for lots of different technologies based on this set of ideas and how moving charges through external fields will apply force to those charges. Good stuff. Physics.